ஹலோ ஹலோ ஆன்லைன்ல செக் பண்றீங்களா? கார்த்தி ஆன்லைன்ல யாரா இருக்காங்க பாருங்க.
சார் கேக்குது. டிஇ பேசுறேன், கேக்குதுங்க.
கேக்குது. முருகன் கேக்குதுங்களா?
கேக்குது சார், நல்லா கேக்குது சார்.
ஓகே 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 வெரி குட்.
தேங்க்யூ சார்.
Okay, I think we'll start the program. Sorry for a few minutes. Good afternoon, everyone. And also, it's my privilege in welcoming you all for this interview lecture. And taking great pleasure in welcoming our most respected and humble Vice Chancellor, Madam joined online, our distinguished guest, one of the illustrious alumni of TNAU course, and the eminent research economist, Dr. TNAU, Professor and Director, University of Massachusetts, USA, the university offices offline and joined online, person heads of the different departments joined online and offline here, scholars, students from cards. Once again, I welcome you all for this one of the very important endowment lectures we planned recently, that is going to be delivered by our best alumnus, Dr. TNAU. So before actually starting the session, so just I would like to indicate some of the highlights of Dr. TNAU. So my fellow colleagues probably know about him, but for the information of the house, the students and young faculty, so just I would like to highlight few things only, because if I would like to indicate his achievements, maybe the day or two I require. It's a very lengthy CV. I would like to highlight very few, the key thing. Dr. Timothy Randir is a full professor at the Department of Environmental Conservation, University of Massachusetts, USA. He is the director of Massachusetts Water Resources Research Center and has served as the director of the Eco Graduate Program for the past 7 years. He is the president of the Southern New England chapter of Soil and Water Conservation Society. Dr. Timothy received a PhD from Purdue University, USA in 1995, and did his postdoctoral work at Purdue University before joining the University of Massachusetts as a faculty. He has a bachelor's degree in Agricultural Sciences from Annamalai University and a master's degree in Agricultural Economics from the Department of Agricultural Economics, TNAU COIMBTORE, the most prestigious one. We are actually very proud to say that the TNAU Department of Agricultural Economics, TNAU, is a leading department in India. That is mainly because of some of the illustrious alumni like you only. It's a proud moment for all of us. Why we say that? We are the leading in India against actually as far as agricultural economics is concerned. So these are all the persons, so the man behind for this. And Dr. Timothy is a consultant to the National Academy of Science, Engineering and Medicine, the American Association of Advancement in Sciences, the U.S. Environmental Protection Agency, the National Science Foundation, and the U.S. Department of Agriculture. In addition, he serves as editor of top international journals like Earth Systems, Climate Change, Ocean Science, Ecological Economics, and Computational Environmental Sciences. Here, actually, here's a long list and very, very reputed publications in many international journals. To indicate few, his publications include a book on watershed management and several book chapters and more than 110 referred articles in top international journals and several professional conferences publications. He has published in top journals like American Journal of Physical Economics, Water Resources Research, okay, Climatic Change, Journal of Environmental Management, many. So the faculty from those days when they were doing our masters and PhD, publishing a paper in American Journal of Physical Economics is a dream. Okay, still I'm not able to achieve it, but so our Timothy had done a lot of publications in reputed journals, and his research extends worldwide, including several countries like Honduras, Colombia, Peru, Uruguay, Mexico, Brazil, Ecuador, Uganda, Turkey, Iran, Russia, China, Indonesia, and some of the countries I feel very difficult to pronounce, so I skip that. Okay, please bear with. And really, it's a very proud moment for all the agricultural economists and all the social scientists and all the faculties of TNAU. So one of our alumni has become very successful researcher in the US universities. It's not easy to get a job, particularly in the research system, okay, in the US universities, and getting a job is not alone. So after that, coming up and sustaining and become competitive with American scientists is very difficult. But in that sense, our Timothy Randir has created a mark and achieved several things in the University of Massachusetts. Really, it's a proud moment for all of us. Okay, and so on behalf of the cards and on behalf of the Tamil Nadu Agricultural University and on my own behalf, I welcome Dr. Timothy Randir to deliver the endowment lecture. Okay, Timothy. So we fondly call Tim. I invite our close Tim to deliver the talk. Okay. Yeah. Now it's over to you. Yeah. And slides on. அது ஓப்பன் ஆகல லேடி ஸ்கிரீன்ல இருந்து அந்த லைட் ரிஃப்ளெக்ட் ஆகும் மவுஸ் இஸ் இல்ல பிரஸ் பண்ணு டக்குனா வந்து இல்ல நான் நீங்க பண்ணுங்க நான் சைன் அவுட் பண்றேன் நான் பிடிச்சிட்டேன் கேட்டல. Thank you, everyone. It's such a privilege for meeting after several years to come here, and
I'm especially thankful for the Vice Chancellor and all the directors of centers, um, Suresh for inviting me to deliver the endowment lecture. And I just want to give a purpose for today's presentation. Um, Today I'll be talking about a very important topic, very generalized topic, which will be of interest to a wide variety of disciplines, but also one of the purposes want to see how I could interact with some of the centers. So there are a lot of directors, deans here. I want to see and explore potential collaborations through this topic. So those two purposes I want to mention. Um, so I chose this topic based on my work. I finished um, my master's as Suresh was saying, 88 postdoc, and but after my graduation, I did my PhD. Much of my work has started to transform into being very transdisciplinary. So it's very interdisciplinary work. So today I'll be talking about um, one of the complex issues when we have environmental impacts and also climate change impacts, it introduces something interesting for research. And what type of decisions we could make in terms of, I called it as smart decisions in the sense, smart decisions are something which can be sustainable. Smart decisions are something which can incorporate complex information. And so I'll be highlighting three important areas of how big data can be used. I'll be introducing one dimensions of additional dimension, often a challenge for research, which is complexity. And third one is uncertainty. Uncertainty is inherent in many of the problems we face in a typical way. Uh, so if you look at some of the symptoms society is facing, from poverty, food security, the economics, droughts, floods, um, rapid changes in resource use, the population changes, and whole bunch of interacting and complex types of phenomenon. Often two things which usually I try to focus on is complexity, how complex the system is. And then the second one is uncertainty. Uncertainty is inherent in many problems. And so I wanted to start off with this mapping done by the World Economic Forum, which if you look at so if just I will just explain. If you look at the x-axis and the y-axis, the y-axis is the impact, the extent of impact of a certain phenomenon. The phenomena can be from cyber attacks to terrorism and a variety of. There you go. So this is the likelihood of impact. This is pretty much probabilities, probability information. So the probability versus the higher impact. So if you look at the mapping of those two, the climate action, the extreme weather, biodiversity loss, all this this red square highlights those phenomena which are emerging to become more important, both in terms of likelihood of occurrence and also the extent of impact. On the left hand side is a map of it's a network diagram of direct and indirect impacts of climate action. This is the climate action failure, which we know that it's a very a long-term negotiation among different countries, but we'll see that some of them are directly related, some of them are indirectly related. So you can essentially see much of the global risk is associated either directly or indirectly with inaction. There it is. Okay. Um, It keeps moving. So I want to highlight with the Sustainable Development Goals. I think we all need to be aware of it. It's such a complex phenomenon. It's a broad uh, framework which has been identified as a guidance for how our global society emerges. So if you start looking at the top one and start moving towards it, you'll see that some of them are very directly related to very complex phenomena like poverty, unemployment, health and well-being, and some of them are really achieving certain resource uses. And so there are 17 goals, 169 targets to achieve, and these are for achieving the goals by 2030. So that means it's by the next decade. And I'll be focusing on one or two important aspects of since it's an agricultural university. I want to focus on the agroecological nature of the problem. So the science of agroecology is some sort of a much more systems-based approach of looking at American farming. Why do we need to invest in? So this quote was from agricultural in the U.S., but why is it very important? And the second one is the role of sustainability, and the third one is some thought of scale. While all approaches are sometimes inconsistent with scales. Scales, I mean farm level, neighborhood level, district level, state level, and all the way to global scale. We need some sort of metrics which can actually transcend multiple scales. And agroecology is some sort of a system-wide initiative has to happen, all the way from resources to the food production to social sciences and a variety of things. And then the focus on the small scale, because whether we like it or not, worldwide the food production is by these small farms, which and the agroecology is some sort of a very high impact interaction with the small farmers. So I've been dealing with complexity for a while. Complexity has been some in front of some of the researchers. Complex systems are something which involve several dimensions, they're not simple in the sense they're having many components operating. Their interactions are also much more dynamic, and they're all having some sort of a properties. Complex systems have the properties of emergence. The agents will essentially, when there is a shock, the agents will emerge into certain emergent behavior. And then they are hierarchical. Sometimes they can self-organize. So think about certain agroecosystems. And there's this shock. Some agroecosystems can self-organize. And the self-organization is some sort of resilience property. And then they are primarily transdisciplinary. I think transdisciplinary approach to addressing complex phenomenon is extremely critical and inevitable. So I'll be focusing on one important aspect on the climate change phenomenon. So radiative forcing and how hydrology itself is a fundamental first indicator of, it's like a canary of a coal mine. So when you have climate impacts, either extreme events, high temperature rises, or variability in precipitation, one of the first thing is the hydrological cycle changes. And hydrological changes cycle is some sort of fundamental for a lot of these ecosystem services on our landscape. So here's from the Stern review, all the way from the left here is some sort of several impacts. This is from IPCC. Pretty much from the food security to water security to ecosystem, extreme weather elements, and then the risk of rapid climate change having irreversible impacts. All this have an onset time. Onset time is when your initial impact is going to be seen in a mild way, and then the impact will start to emerge into becoming much more intense. This may not be true, but this is just a regional impact of certain. So one of the interesting impact is every region has different implications in terms of climate impacts. So these are representative risk for each region, from glacial melts, runoff, flooding, droughts, um, impacts on marine ecosystems, wildfire, terrestrial ecosystem impacts, impacts on food production, all this red one here, and then the livelihood, especially impacts, direct impact on health and livelihoods. So if you look at how the countries, regions are impacted, they are highly variable, and also some risk will predominate certain regions much more than others. I'm going to skip few of them. This is the global map of the direct impact. So when we see floods on one side, droughts will be on the other areas, will be endemic in certain regions. Glacial melts will in other places. So it's primarily excesses and deficits operating simultaneously in different parts of the world. The primary drivers of the impact. So this is from assessment report 6. Pretty much whole bunch, variety of implications from coastal, terrestrial, freshwater, and variety of. These are for policy summary for policymakers. In terms of regional, how many people in millions are going to be affected? So one important is both the watershed level, which is the landscape impacts in terms of water resource stress, to increased number of coastal floods. Asia is some sort of a high prime area in terms of where these impacts could be seen. And why I'm talking about that is these impacts also shows that where our future investment in research or teaching and even entrepreneurship investments, it opens up a lot of opportunities for us. I want to highlight the implications on food security. So pretty much much of the crop yield losses in 2030, we see that many of the crops are expected to have losses in yield. So that means our production levels can go down. These are some of the example crops: maize, rice, wheat, bean, and pasture for beef and dairy production. So all of them are expected in all the continents to have some sort of a substantial decrease. This one actually challenges in terms of how do we incorporate adaptation? How do we build in resilience to the systems? So in terms of the prices, so this is part of trickling through the markets. So what do we see in terms of the market behavior in terms of this adaptation or the shocks in the system? From maize prices to all the way to other crops and wheat, there will be like some sort of market increases in terms of price increases, or sometimes it will be offered in a very difficult to be offered by those who are in the low income. So people who are worst affected or developing economies, where people spend a lot of amount of percentages for food production. That means the affordability for food will be seriously affected. So I'll skip few of them. These are some sort of a documentation of the role of water stress with and without climate change. So one few elements in terms of direct effect on agricultural productivity. So even though I'm showing examples of the US, these are equally applicable in many of the production regions. Frost-free seasons, especially in the north, the frost is a very important date when the growing season ends. So when you have change in your frost-free season, if it starts to increase, that means it has a direct impact on which season we can produce. Change in the number of consecutive dry days, that means you face dryness in soil moisture for a longer period of time, hot nights, and also frost days. So all this have direct implication on the production regime of. So a lot of vegetables on the in the San Joaquin Valley in California, there's a lot of Midwest produces huge amount of corn, hog, and so all have direct implications. So this is focusing on one central valley, on different production of rice, wheat, sunflower, cotton, all have some sort of expected decreases in yield, crop yield. The crop yield decrease can be because of the stress related to soil water and soil moisture, increased rainfall variability, and so here's just zooming into a lot of regions for these four major commodities: wheat, rice, maize, and soybean. In both 4.5 is the representative conservation pathways, and 4.5 and 8.5 is the worst case scenario. In both the best and worst case scenarios, we see that all these commodities will have changes in their production rates, decreasing, and also the projected one for until 2050, both in percent changes in production and in will start to show direct impact of climate change. So said that one, that just probably very familiar, but just a reminder that those are emerging challenges for researchers. I'm focusing on this research more focused more on the food production side. So what are the research and decision themes? Big data is some sort of a falling in our lap, in the sense we are collecting so much data, either from hydrological, ecological, agricultural production systems, climate systems, and even on the social side. So we have so much of social media data sets, and how do we use that one, use some sort of artificial intelligence to actually make decisions quickly. Sensor networks and monitoring is becoming another really important one, so that we recognize a particular risk early and also respond to them quickly. And the big question is the decision when we face uncertainty, what type of decisions we could make, and how do we make those decisions? So I will give you some examples of research in that decision uncertainty. A lot of times our optimization is very simple. We optimize for increased profit or increased income levels, or one attribute, increased yield. But a lot of times when you talk about sustainability, it is always multi-attribute. So we'd like to have good quality food, good yield. We also wanted to have least impact on the environment. We want to have less amount of toxic chemicals applied. So this opens up multiple attributes, and how do we optimize that one? And a lot of times optimization now involves challenges on the social science, especially those who are economists. How do we quantify those objectives which are multiple? And then so much of my work has been trying to actually interface between this big shock, the climate change shock, to the watershed systems itself. Watershed systems is some sort of, I invested my, after I graduated and went to my PhD, I did a lot of work in watershed systems, because the watershed system is a very challenging area, and that's only because it's interdisciplinary. It always demands huge amount of mathematics and quantification. It's very dynamic, and trying to actually figure out how the system is moving and how it's actually changing with certain shocks, whether it's a land use or climate, was some sort of very appealing for me. And so if you look at a lot of my publications, you'll see that it's actually studying this watershed system, both for water supplies and water quality aspects of it. Uncertainty has been, in the past decade, I've been tackling uncertainty in a sense. Uncertainty is, we do risk modeling. Risk modeling uses some of the probabilities to actually come up with some really interesting outcomes. But a lot of times we are also challenged with one scenario where the probabilities are very low, but the damage is much more higher. So these are extreme events which usually used to occur more than 100 years, once in 100 years. Now they're occurring more frequently. So how do we capture those types of things when we have less amount of information? We have less unengaged watersheds. When there's no monitoring possibility. So that's where remote sensing, some sort of simulations, all those things come into play. And then I'll be also talking about the multi-scale ecosystem framework, which I developed maybe 4 or 5 years ago, which is really appealing and has been used for many of the governance type of policy. So I'll give a quick overview of the big data and artificial intelligence, and more focused on remote sensing applied to environment systems. So big data is some sort of a, as I was explaining, we are generating so much monitoring data. We are observing a lot of data sets which are spatially as well as temporally exploding, I would say. And that's a huge potential for
Friends, those who are attending online, kindly mute. Please don't talk unless it's disturbing. Please mute all of you. I request all of you to kindly mute your mic.
Thank you. You can. Okay. Sounds good. Hey, sorry about that. It happens when we have a remote audience there. Um, so this big data is also, I wanted to mention the nature of the data itself. It's high volume. It also is very rapid. That means every few seconds and minutes and even hours, you will actually see a lot of the high amount of rapid increase in the data itself. The data itself is variable in the sense a lot of variety of data from social sciences to ecological sciences to agricultural sciences to meteorological variety of domain. And this sometimes we are seeing that those who are familiar with the climate change models, we used to run the models. This was long ago, maybe 3 decades ago. I would say it takes several days and months to actually complete one single run of a climate model. But it has been changing. Nowadays we have very fast computing, and so you can run it in very few minutes. So that means we are also generating, even in remote sensing, we are slowly encroaching into higher and higher resolution. So initially the climate models are 1 kilometer or 100 kilometers, and now we are starting to predict at a much more higher level. And the remote sensing, you can see that some of the hydrological models, which used to be 250 meters, now we are aiming for 30 meters or even 1 meter type of resolution. So that means, think about this, it is actually exponentially increasing the number of data quantity itself, and how do we analyze it to make informed smart decisions. And lastly, the multidisciplinary research and the workflow. And again, the multidisciplinary research, when you add information from multiple disciplines, now there is differences in resolution, differences in how we define certain things. All these things are some of the challenges we face. Specific applications related to this is forecasting is a really important area. Trying to actually predict what will happen, and now it's not just for weather elements, but also to see how the yield will change, how will the economic markets change. And then early warning systems has been a big investment in whether it's a floods or drought, or even tornadoes or hurricanes. Early warning systems, how quickly those systems can warn us to actually make predictive actions. Disaster management after a petrol disaster occurred, how do we invest in and also develop strategies so that the damage is minimum. Smart environmental monitoring system is now becoming very common. I'll be explaining one of them. These are monitoring systems exclusively designed to actually assess certain dynamics and fluxes of certain systems, but also developed as a network so that it's actually fed into some control systems where the monitoring itself is enabled. Energy management systems, application also again based on reflectivity, but and also how energy budgets itself change and how they could be captured by remote sensing and now big data analysis. So one important one often I'm involved in is the remote sensing applications related to land cover changes and how it can be predicted. I'll show you one example. Impacts on water quality, changes in the sources, and also how stress detection can be evaluated. And then some of the other ones, primarily quality assessment, where it's nutrients, nitrogen, phosphorus, primary productivity on the coastal areas, all these can be remotely sensed. And so these are some of the interesting ones from remote sensing has been used on the big data types. And so one thing I want to give you an example in hydrology is the GRACE is a really interesting satellite data set, often very used in studying groundwater fluxes. And that is some sort of another interesting application of remote sensing. And again, it's a huge amount of data set for the whole world. And using that to actually capture the dynamics of how groundwater is itself shifting. So, but anyway, here is a variety of application listed here and what type of data are available worldwide. Okay, so one of the interesting application is these types of deep learning algorithms. Again, why I'm putting that one is the algorithms are there are a variety of algorithms. We are constantly fine tuning certain algorithms to actually make our decisions much more effective. But these available algorithms has to be tested under different conditions of problems available. So, and these algorithms are already constantly being improved over time, but those who are applying it often we have to test some of those and then compare and what works. And so, for example, the CNN is the first one is really popular, but you also have other ones which are emerging into becoming much more efficient in explaining the data sets. So these are some of the examples I want to mention that one. So I want to focus on applications of these algorithms. For example, the CNN, the convolutional neural networks are really good in terms of applying for satellite images, processing some of the sensor images, forecasting time series, that type of applications. The long short-term memory networks, again, really used to learn and memorize certain long-term dependencies within your time series. So some of these, pretty much you can see that if it is involved certain video enhancement or image recognition or high-dimensional data, you have different algorithms which work much more effectively than others. So here I will shift my focus into some of the applications. So here is an application of predicting stream flow using machine learning. So here is the Connecticut River watershed, which is one of the biggest watershed in Northeast. That's where much of my research has been in that area. And so this one has a lot of variability in terms of stream flow, also has some flooding regimes because many of the settlements usually are along the rivers, and that is one of the typical interesting societal phenomenon that people would like to be next to the rivers. But rivers also have floodplains because they need the floodplains to actually mitigate the flooding. So that is the paradox, I would say. In coastal areas, people would like to settle, but coastal areas also have high amount of sea level rise impacts, shoreline shifts, hurricanes, tornadoes. So, but still, we would like to be there, right? It has a complex behavior associated with economics and insurance and our own values related to being next to water. Um, so this one is using gradient boosted regression trees, primarily trying to actually predict stream flow based on temperature and precipitation, which are climatic drivers. But there are some of them are some sort of there is a both lagged effect, but also the precipitation and temperature simultaneous effect. And this is some sort of prediction on how the stream flow is actually observed stream flow versus the predicted stream flow. So it's reasonably, it does a really good job of predicting the stream flow with available data set. Deep learning and temperature. So when you look at landscapes, one of the interesting thing is you have tree cover and vegetative cover. Think about COIMBTORE, how the city itself has changed in terms of impervious cover, the buildings, parking lots, and everything, and then the loss of certain forest cover and vegetative cover. All these have some sort of feedback, mechanism on times on how temperature changes locally. And so deep learning, this one is using deep learning to study the interaction of impervious coverage as well as the canopy on studying how it influences temperature. So this study is another big data study done with the colleagues in Iran, trying to use Google Earth Engine and G1. G1 is some sort of a spatial data sets developed by NASA, and using that both to study temperature anomalies on the surface temperature anomalies and anomalies, and using some sort of a process in modeling, capturing at a much more spatial level, but also study some sort of a seasonality and also the trend on how it's changing. So I want to mention these examples in a short one slide. Just for you to actually think about potential application of big data in natural resource management. So here is sensor networks. Sensor networks are primarily trying to actually having a network which will actually track a particular process. So this sensor network is for water supplies. So this is a water supply challenge. It was given to a whole bunch of researchers. So there are 15 design groups who were asked to actually have these objectives. You have to reduce the expected time of detection, because if there is a contamination, you wanted to have it quickly detected. Reduce the expected population affected prior to detection. That means if your sensor is not sensitive, how many people are vulnerable and exposed to before its detection happens. Also minimizing the expected consumption of the contaminated water prior to detection. And then detection likelihood. This is the one which is maximizing it. Maximizing. So this is a multi-objective one given to this 15 groups to study, and they have some sort of a mapping of what the design challenges come up with. So here's a design challenge directions. Often the design is not just for water supplies. This can be designed for any type of environmental process. So contaminant warning systems, evaluation, aggregation is another one. So you don't want to have sensors, thousands of sensors all around, because that's not economical. Sometimes you'll start to see that there is some sort of a economics of sampling. There is an economics of sampling. So reducing that complexity. Again, in sensor network design, what is the optimal number of sensors, but where they should be placed? Some sensors can be multiple use. That means you can study a variety of things within one type of a probe. And Some of the threat ranking, risk assessment of networks, all these are some sort of emerging direction of sensor design network. This was a study I did in Uganda in the Kampala city. One of the complexities there is, so you have a water supply network. The water supply has to be has to handle E. coli contamination. So E. coli, Escherichia coli is primarily is responsive to chlorine. So that's why we add chlorine to reduce the contamination. But the chlorine concentration has to be ideal or maintained. If the chlorine concentration is high, it results in chloramines and it's toxic. If it is lower, actually E. coli will increase. So people will become sick. So again, this one was a very interesting study on seeing how each individual nodes, the chlorine concentration is changing, and also how to optimize it so that this whole system is having the ideal levels of chlorine. This might be appealing for economists and extension research. It's primarily how to develop a multi-objective, and I have been working on the MOUT, which is the multi-attribute utility theory. It's primarily having a variety of objectives, and each one is generating a utility. And sometimes you can have additive utility, that means adding up all those individual utilities, or it could also be multiplicative. And then resulting in an optimization, multi-attribute optimization. So this type of multi-attribute optimization structure is like this. You have the system conditions on the and the as constraints, and then we have the function, the multi-attribute function as the objective function. So here is a spatial optimization application, essentially saying there is some sort of a unique efficiency in terms of optimizing over space. So think about a watershed system where there's a dynamic interaction happening from the headwaters to the outlet. So your dynamic processes, the cell which gets at the end is dependent on the cells which are draining into it, and then and so forth. It keeps on going until the boundary. So when you have the dynamic process, it's very difficult to optimize. So you have to actually optimize downwards and then optimize that string of elements, and then you use that optimization and then move to the other one. So dynamic optimization is applied to spatial optimization in this case. Other one in this was published in Water Resource Research, is finally trying to look at how those trade-offs emerge as we increased certain things. For example, if you change your land use to land use, it might have an effect on water quality and habitat, but it also has some sort of cost issue in terms of you losing certain opportunity cost. And so all these trade-off functions are very useful for decision making. So one interesting application, this one is in Massachusetts. So you can think about each one of those areas, you can break it into sub-watersheds and think about each sub-basin as an agent. If I ask you to actually have some person managing that specific sub-basin, there's a whole bunch of attributes they can. So it's like a performance metric. So each sub-basin can actually have a performance, and now this performance can actually be entered into a tournament. That means now we can say the best performing sub-basin now will be the winner, and now it enters into a game theory. So the game is now, so that particular sub-basin gets the high priority. So let's say this one is the winner. Now all of this will now have the incentive for them to come there. So it's like a, so one of the leading experts in water resources actually was saying that this type of performance metrics are critical for water resources because it's like a GPA. your grades. It's a really powerful one to give us incentive to work better, and so that is just actually applying it for resource use. So this one is an actual application of climate and land use. So you have these two drivers simultaneously operating. So we see a lot of research in climate impacts on watershed systems or resources, but land use is also having a big impact. So when you have both of them operating, you have a synergistic impact on resource conditions. So this one is actually studying using simulation models to actually study the impacts of climate. So this one was actually calibrated for actual observation. So it's pretty good observation calibrated one. And then you force so this is for land cover change. What type of land cover change is predicted and what will be having the impact. So this one was predicted using similar automation, so that you can know what type of land use change will occur in the future, both migration. It also uses the past land policies, what happened historically, the changes, and so use that information to predict into the future. And so land use on the left side, this one, the climate impacts, and now having combined impact has a different synergistic impacts on runoff. So here is a simulation of actual runoff. Runoff is actually both at the land use levels. So this is just a spatial distribution of runoff under climate stress as well as land use stress. So here's the big data analysis related to uncertainty. Uncertainty is some sort of, as I was saying, is endemic to a lot of data sets. So here's on the left-hand side is the data sets related to climate, but it's a very vast data set. But one of the question is, how do we map the uncertainty? So mapping that uncertainty over space and time. Is our uncertainty increasing over time? That's a temporal question. Is it changing over space? That means if you have a risky center, is the risk increasing around it? So that's the spatial uncertainty changes. In order to calculate that, there's so much of mathematics involved. So you have to write your own script in Python and ArcGIS. And so here is some sort of a space and time distribution. So now from 1950 on, all the way to 2099, how temperature is actually changing over space and as well as time. So it's slowly increasing in the space itself, but also over time it's actually changing. So here is a actual mapping of the temperature itself and then the variability of the temperature. This is the variability related to spatial variability. Same thing with precipitation and its variation. So that is a big data analysis, and it's very useful to see the trends. And one of them is this black swan is some sort of those who are in economics, I want you to look it up. So the black swan event is something unexpected, and usually it happens like in stock markets and everything. It's a really interesting one. But it is interesting for us, for this question is the question of Bangladesh. Bangladesh had a really interesting case of arsenic. So arsenic was some sort of in the water, and it takes 10 years for people to get symptoms of arsenic. So initially what happened is when people were drinking from surface water, they said, don't drink surface water, drink from the well. And then everyone switched to well, and then the wells started to show arsenic. And still the symptoms take 10 years, so you cannot predict to when your source is coming. So the wells, these are shallow wells. And then they said, no, so don't drink from the shallow wells, drink from bore wells. And then the people switched to bore wells, and bore wells also showed arsenic. So it's very unfortunate because Bangladesh is in a deltaic area. So a lot of arsenic is coming from Ganges and the rivers like Brahmaputra and everything. So it's actually having sediment loaded with. So even if you drill deep, there's a geological source of arsenic. So the question is, in terms of decision making, there is surprise because you're surprised by certain events. That means you didn't expect it. Hurricane Katrina was some sort of a surprise. Hurricane Katrina in New Orleans was a huge surprise. They didn't have any hurricane before, and all of a sudden it was devastating. So that was a black swan event. So how do we make decisions in black swan events? Is primarily here is there is a very old theory in terms of surprise, isoattractive curves, and uncertainty. And so I used to develop that one and applied it. Um, so it took some this potential surprise framework. Potential surprise framework is very interesting because it's not risk modeling. So risk modeling, if you have probabilities, you multiply with probability and maximize, minimize, pretty much easy. But here, surprise is very difficult to quantify. And so when we applied it to Bangladesh, it came out the same, being that when you're facing risk, diversification is some sort of ideal strategy. And that's what it showed up even in surprise phenomenon. So diversifying, that means don't drink only shallow waters or surface water. You have to actually diversify so that the risks are minimal. Another big question is, so many places we don't have information. They're remote. For example, Amazon jungle, so we don't have information. Some islands in, like, say, for example, Papua, where my student is working on, they pretty much you cannot access it. You cannot go there. So how do you make decisions in those areas? So this one is actually in Russia, where the watershed, we don't have any observations. So in those cases, we have to make predictions on that. So this research was trying to actually simulate evapotranspiration, simulate climate impacts. So this one pretty much was very useful for decisions in terms of which areas will face climate impacts. So this one is a huge watershed in South America. It's a Orinoco watershed. Colombia is right here. And then this is Venezuela. Venezuela is, so trying to actually simulate, again, this is a very difficult area to actually go measure. So you can actually use simulations to actually see how much runoff in those areas are. And this is using the simulations to develop some sort of ecosystem service index. Often very useful to highlight which areas need investment. I want to highlight this one. It's a really interesting one, bringing in scale effect in a lot of planning. So here is for at farm level. So you have manure generation, but farms usually cannot handle manure. So usually they actually move it around. But farm manure application also has impact on regional nutrient status. So this one is actually simulating what will happen, the hydrology and the nutrients, nitrogen and everything, with and without manure application, and trying to see which subbasins have high amount of pollution load, just purely because of higher amount of nutrient. So there is some sort of the ecosystem science associated with some of these watershed systems. So that's for nitrogen simulated, and this is the phosphorus simulated. And then you can also correlate with stream order. Stream orders are first order streams, second order streams, and see which order streams have a higher amount of nutrient loads. And for the temporal variation, that means looking at the several years of data and how much standard deviation and variation is occurring, and you can also map those variations by spatial units. So this for that's for the phosphorus. So those are some sort of a quick overview of certain small projects which I have been working on, which apply some of those concepts. But I want to highlight some theory which has been, which I developed based on the resilience itself. This is the multi-scale ecosystem framework. So you're all familiar with the role of scales. Scale is primarily you have a small farm, neighborhood, district, state, nation. So everything is actually connected to each other. So any policy development should actually be responsive to scale. So you can develop a national policy, but if the national policy is not looking at global scale or even sub scales, it becomes very inefficient. Even though it's easy to just ignore other scales don't exist. So in a lot of socio-ecological systems, your persistence, the change, and unpredictability are some sort of a characteristics of the socio-ecological systems. The disturbance sometimes can be observed and absorbed, and the system itself self-organizes. But many times systems can actually transform. So there's a huge stress from extreme event. The system cannot come back to the original condition. That means there's less resilience, and it will be transformed into a new type of a system. So, so here is some sort of an example of high multi-scale ecological and multi-scale socio-ecological, which actually looks at a variety of scales. So based on that, I developed this multi-scale ecosystem framework, primarily looking at both ecological and economic systems, but cognizant of each scale should be referring to the upper scale and the lower scale. It's a big challenging one in terms of governance, developing governance for it, and it also is some sort of a challenges ourselves to think about how we can actually handle resilience, which can actually be sustainable. So one application I used in this one is some sort of impact of globalization on certain resource use. So many developing economies are saying she has a huge amount of drivers coming from globalized economies. Palm oil plantations are becoming expansive, having huge impact on the local economies. Coffee is another interesting coffee market. Working on a project on coffee markets, on how coffee is produced by small farms in many countries, but it also has some huge amount of supply chain issues and price spreads and huge damages in the local level. Removing a lot of tropical forest to actually use it for drying coffee drying. So, so this multi-scale framework will be really useful in terms of trying to build in those scale elements, the complexity itself. So in terms of policy design, the cost becomes a fundamental factor in terms of what are the options we have. Of course, we have everything we can actually deal with, but some of them are has some sort of per ton large amount of cost involved. Like say, for example, coal to gas shift has huge amount of cost versus others. Building insulation has some sort of a reasonable cost reduction, especially to reduce greenhouse abatement. So again, this one opens up the role of economics and follow into a policy design. Adaptation and mitigation are two things we're all familiar with, no action, but adaptation and mitigation has to be within the framework of sustainability. So that's this what so we have cost of mitigation, cost of adaptation, but if it doesn't include sustainability concepts of environmental, economic impacts and social impacts, often it becomes very inefficient. Again, those are some very important specific areas of research, whether it is in agribusiness, biological systems, even in social systems and plant breeding, genetics, variety of things. And we always try to achieve these adaptation mechanisms within that one. So some of them will be long term, some will be cost will be very high, but I think that pretty much this multi-scale approach should be a critical one in terms of addressing these types of stresses. policy evaluation. I think this is some sort of a quick chapter, chart which helps us to actually look at the complexity. So the last column is political feasibility. Political feasibility is some sort of we have political cycles once in 4 years, often driving many of the investment decisions. Then you have administrative feasibility. Then you have all the way then is the environmental effectiveness, economic, and the middle one is often a big challenge, equity. The equity, that means the distribution of the benefits to the society itself. So voluntary type of policies, information has some sort of a effectiveness, very limited in terms of um, willing voluntary application, but it takes time because it actually depends upon education. But you have regulation itself you can get good amount of effectiveness, but political feasibility and also economic feasibility is poor or sometimes good. So then you have all these interesting instruments which can be helpful for us to evaluate how we are actually achieving within the framework of the feasibility structure itself. So I just want to conclude there. So we have some of those technological institutional structures, and adaptation at each scale is extremely critical. Household to global. This is the conservation and the use of data sciences to build those some sort of a connections which can transcend across scales. Early warning systems, which are fundamental, and even disaster management, which is having efficient way to address some multiple scales. Cooperative systems, that means institutions and building cooperative information is big at a system scale becomes very important. And also lastly, I would say that it has to be a robust application of data systems so that we can come up with decision systems which are very effective in addressing some of those. So that's why we call it as a smart decisions. So with that one, I will stop my presentation. But definitely, I encourage you have questions. But also, I want to encourage directors to share how we could actually work. These are some things I have been doing, but there should be some area where we can actually always collaborate. And I'm looking for developing a MOU with this university, and I want your help and your cooperation to actually find one specific element which we could actually collaborate. So I'll stop there.
Thank you very much, Mr. for having given a very vast and exploratory and detailed lecture covering different domains on climate change issues, big data, multi-attribute policy modeling, everything. So now the floor is open for questions and discussions. First, I think first we have questions from the audience, and then we have some kind of discussions, and then we'll also discuss for possible collaborations. I think this will go fine, right? Yeah. Mike. No, mic எடுத்துக்கூட.
Welcome back, POP to TNAU. Okay. So glad to see you after 32 years. So you have mentioned you did some work on evaluating the impacts of climate change in land use or using temporal data. But the land use varies due to several factors, due to urbanization, due to lack of water table, due to changes in everything. But how we segregate the land use changes is according to because of climate change. That is question number one. Then question number two, I was surprised to hear the term potential surprise. Okay, we define risk and uncertainty where risk we can measure the probability of uncertainty, in uncertainty where we are not able to measure the probability. But how do you distinguish, this is for academic purpose also, how do you distinguish between uncertainty and potential surprise? And is a potential surprise, if you are going to evaluate, there should be a little of element of predicting the probability without, what is the measure I didn't, because I am curious to know what is the basis on which you are able to predict that there is a potential, there is going to be a potential surprise. These are the two questions. Thank you.
Thank you. These are awesome questions, you know. So I did two types of models for land use change. So one is a model which actually has those assumptions to make predictions based on the past. Historically, if you have land use policy and what happened to transformation, so think about a one cell which is getting transformed. It changed from forest to agriculture or agriculture to urban area. So that has some sort of a memory. And that memory is the one which was used in one of the studies to what we called as a cellular automation. That means you allow random seed on the landscape, but allow those each cell to move through some sort of a transitions using a transition probability. So that was one of the approach, assuming that the past is a predictor of future, but future may not be the same as the past, right? In those cases, the assumption will fall through. So that's one thing. The other approach, which I think I showed you here, is it's actually a study done in Purdue University, where they actually used at a district level and also a neighborhood level to using census data to see how land use is actually dependent upon different factors from in-migration, out-migration, the drivers like prices, like for example, forest prices to agricultural prices to urban rents. All these are actually factors that are used in this prediction, and you actually predict it into the future. But I want to put a caveat to that: is it's extremely difficult to actually predict land use.
Okay, how many years data we need?
So a good estimate of the number of data years you need is, say, let's say you have 30 years of data.
Okay.
You can actually go into the future, maybe half of it, like 15 years, in order to get good probability information, or at least confident, but you still cannot get 100%. The main idea is to move in the expectation range. That's what in statistical modeling, we calculate expectations, but we'll say how frequently we can enter into errors. So when we project into the future, it has to be, we have to be very clear. As we move farther and farther into the future, our reliability of the data will be lesser and lesser. So that's one thing. For the nature of risk and uncertainty question. So we often, many of the researchers will use risk and uncertainty for the same behavior. Like for example, they use uncertainty for risk behavior or risk to uncertainty. So they don't differentiate. But Knight was the first researcher who is from London School of Economics. He was the one who actually brought out saying that those are two different ones. So if you have good probability information where you can actually do probability risk modeling, that is usually should be classified as risk events. And those we don't have probability information should be called as uncertain events. And he left it there, but there was no alternative for this uncertainty modeling because you don't have any information. So the surprise, so there's also not sufficient theory to actually guide us in this right-hand side, the uncertainty one. Because we have the good probability theory on the left-hand side for the risk modeling. We don't have a suitable one because in surprise and uncertainty, the wealth can go negative, positive in all directions. So this surprise theory was something which was developed by long ago, uh, which was actually based on the probability theory, but it was not applied because it's very complex. And so the one question coming to you is how do we know if something will happen in the future when we don't have information in the past? We often depend upon experts, experts. So usually expert opinion is the how we actually move forward in those estimations. So for example, we ask biologists, ecologists, hydrologists, meteorologists as a group to come and estimate what is the likelihood that there will be a extreme event like a which haven't happened before to occur in the next 5 years or 10 years. So use those types of evaluation to come up with some sort of additions on those estimates on what is the potential likelihood. So that's the only way we do that. The other one is scenario analysis. And scenarios are some ways we actually will say what's the less likelihood and the maximum likelihood. That's what we do with climate change studies. Is we have the representative concentration pathways, and we make a lot of generalization about whether the countries will come together, whether the industry will adopt carbon neutral technology, or so. This is scenario analysis. Those are two important ways we could apply potential surprise theory.
Okay, thank you.
You can ask any question. I think. Yeah. Yes. Even if it's with the subject.
My question on behalf of PhD student, I am asking you can take some of the PhD student in dynamic optimization, especially water surface.
What is
So no thesis have come on dynamic optimization, I suppose so.
Yeah. So dynamic optimization is a really interesting one. Um, so think about this. If you have a time series of your wealth and you're trying to actually um, optimize your cumulative wealth in a particular time stream, it's not easy. You cannot just add it because the wealth in 1 year is actually being influenced by the wealth in the past and the wealth in the future. So there is some sort of a dynamic interaction happening between years. So what happens is you move all the way to the terminal year. That is the what we call as a bequest value. And then you say, what should I do to maximize that value in that particular year? Let's say it's 30 years from now or whatever it is. And then you optimize it, and then you use that one to actually model the previous year. We call that a T minus one, right? Um, and then once if you optimize those last 2 years, use that one to actually optimize the previous one. So, and then by doing that iteratively, you end up with a optimal dynamic programming solution. Why we do that systematically is if you try to optimize the whole time series, we have a problem in computation which is called as a curse of dimensionality. Curse of dimensionality is as you're trying to optimize, the dimensions will start to explode. They move exponentially. To solve it, the dynamic algorithm, this is like from Bellman, it's primarily systematically solving one stage at a time. And that's the dynamic programming optimization one.
Actually, to supplement Timothy, actually, few of our studies they have done so the dynamic optimization, particularly in the groundwater. So they employed optimal control theory, and so they optimized. They are done, and but not so only groundwater, but not in other domains. But probably, so if someone is interested in working on some forestry kind of thing, so they can, and the environmental pollutions they can do it.
Sir, good evening. Sir, in our study, it's GHG abatement cost post to 2030. When you have plotted a carbon equivalent and euro per ton. Just I want to know what's the carbon trading situation, current situation in USA as well as India. That's it, sir.
At least I can talk about US, carbon, so many states now have a objective of reducing the carbon footprint by 2050. So they want to become carbon neutral. And that's a really, I some sort of question it in a broader sense. When people call as carbon neutral, what they're talking about is they're doing carbon offsets. Carbon offset is, let's say you have electricity produced and you're buying electricity from coal burning plants. Instead of buying from coal burning plants, you buy hydropower from somewhere else. And then you showcase that much amount of carbon has gone down. And the funny part is you're shifting the burden to other countries. In the US, in the state of Massachusetts, so we have by 2050 they want to have come to a carbon neutral society. And what was there is primarily buying a lot of hydropower from Canada, and that hydropower plants are located in indigenous communities. So these are indigenous community land, and they're going to build dams there. So that you're shifting the burden to some indigenous communities to actually achieve certain carbon neutrality. The other one is carbon neutrality doesn't mean that there is complete carbon neutrality in the state. They are actually, it's accounting type of a strategy. You buy offsets from South America, you buy offsets from somewhere else, like a wetland conservation area, and then you showcase in your accounts. And really, in a physical sense, you still have carbon pollution there. So it's really, so those are some of the critics of my in terms of those strategies. And your question about the abatement costs is, it's just like any other any technology. We have the cost structure. Those in economics, you'll see that there's a long-term cost and short-term cost. Many of them have very high cost because of huge amount of investment needed and negotiation needed. There should be ratification of certain agreements. All these things will increase, make it much more higher cost. It could be also technological costs. So a good example will be trying to find water source. The easiest, the cost effective one is the surface water source, because you can just catch the water with gravity. But you can also do it with groundwater. In those cases, you have to pump it. So you have to spend money to that. So the cost is higher. But the highest cost one is going to be some sort of a towing icebergs. There are icebergs in elsewhere. You could tow it and put it next to a city and then supply water. That also involves huge amount of cost. So desalination is another one. Removing the salt from water, it is a very high energy type of input, but also investment cost is very high. So your cost of per gallon water is very, very high. So that's one of the example of all these options. If you don't look at the economics, it will become very difficult and inefficient, I would say, to just throw it certain options to achieve certain reductions. So those are actual observation, or the per ton reductions are actually calculated ones based on the technology and even the social values itself. So I don't know if I answered your question. Oops.
So good evening to all of you. Really, it is an excellent presentation, sir.
You have covered everything about A to Z, climate change and its impact, big data analysis, then models, resilience, mitigation, policy evaluation, etc. So our Vice Chancellor is very much interested to do the collaborative project, and you also expressed your interest. So after hearing your lecture, I have an idea to propose the collaborative project proposal, that is through the multidisciplinary approach on creation of climate resilience in Tamil Nadu semi-permanent river basin. Why? Because in Tamil Nadu it is a 17 river basins are there. Among that, the two Tamarabarani and Kaveri, these are the major river basin, and also it's the most important, and it covers major command area. So this is these two basins are already well studied for this climate resilience during current and also future. But other 15 river basin need to be studied to make a comprehensive policy, sir. So any chances there?
Yes, I'll be glad to collaborate in any specific way, because in the next month or so, I'll be having a MOU between University of Massachusetts and our university TNAU, and it opens up a lot of opportunities for research collaboration, student exchanges, faculty exchanges, and I think for research collaborations, I think it'll be wonderful to, um, especially I think it has some win-win situation. That means um, uh, I've been I have my own lab having a lot of expertise on trying to actually model, simulate variety of conditions, but also it could be used to train a PhD student here to work in that particular basin and have me as a part of the examination committee, or so that I can guide and we could accomplish that one. So those which are not studied well, I think it will be a win-win for both the university. Absolutely, I can do that.
Thank you, sir. Thank you. Sir, I have one more question. Actually, India is having organic and microbial approach in farming compared to Western countries. So how it is considered for future projections?
Um, so one of the the organic farming comes back into some sort of a, it's not a production is good and the production side of things, but one of the thing is the certification level. How certification level. So primarily, you can have a certification that it's organic produce, but who is going to monitor it, and what is the truthfulness of that certification? All those things are big questions, and that's why I think many times some of the organic produce are some sort of label, but also it also very high cost, but people are willing to pay when it is genuine. So unless that certification is actually inspected, studied, so that that certification is 100% true, then only I think it will become successful. It's like a product differentiation. Not just by just labeling, I think we can achieve it, but I think the most important one is I've seen in US struggle, it's struggling, the organic agriculture. USDA is pushing it, but one of the biggest challenges is many people don't trust that and how it's produced. People can apply herbicides to clear the land, and then after that they don't apply pesticides or anything, but still it was having herbicides there. But the produce is now the whole production chain itself has to be looked at, whether it's organic or not, and certification by external agency or anything becomes very important. So that's why, but I think there's a lot of scope. Many countries I have visited, small farmers are very much interested in investing in organic agriculture and sustainable agriculture, because there's one huge amount of demand. It's much better than traditional agriculture, where it's a lot of huge amount of excess fertilizers, heavy amount of water use, heavy amount of pesticides beyond what is recommended, and even clearing forests itself, huge amount of damage to the local ecosystem. So many farmers are really interested in producing organic organic farming.
Thank you, sir.
Dr. Timothy? Yes, Dr. Suresh?
Hello.
Velayudham Dean from Tanjavur.
Okay.
Hello.
Sir.
Yes, Suresh. Is it audible?
Yes, go ahead.
Hello. Yeah. Good evening. Excellent presentation. My congratulations to Dr. Timothy, my junior, Timothy Randir, my junior, and everybody, they got benefited through this lecture. So my concern is now the Kaveri Delta, we have the rice crop as a major crop, and it feeds the entire Tamil Nadu. And we have a situation, two situation. One is the old delta situation, another one is the new delta situation, wherein the soil permits only for in the case of old delta, the soil permits for the cultivation of rice. But earlier, if you just look at the cropping pattern, it is rice pulse. But now because of the changes in the water availability, it has been changed as rice pulse. And now the surface water is also not available here. Entirely it is getting water from the delta, the Kaveri. And the soil doesn't permit to go for any other crop. So the change of crop is not possible. So as per your predictions, in the year 2080, there will be a change in water supply also. So we also expect that in the coming years, owing to the water supply variabilities and shift in the rainfall pattern, the cropping pattern may get changed, but there is no other option for the farmers of this region to go for other crops in the heavy clay soils except rice. So my request is, shall we have a collaborative research to develop a design for delta region with an eye aiming on food security of the state in the 2020, because as per your presentation, the price of rice in 2080 is going to be increased by 89%. Shall we have a collaborative work? Thank you very much.
Absolutely. I think that's a really good question. It's exactly the same thing Bangladesh is facing too. So they don't have any options because it's also a delta country, area. There's not many options. In terms of adapting, how do they adapt if they don't have alternatives in terms of crop structures? Um, and I'll be glad to actually collaborate in trying to evaluate um, strategies and what will happen if we have a clay soil. What are some of the other enterprises they can they can switch into, um, and also trying to predict what might be the rainfall regime, flow regime, and we also have the conflicts happening. So when you have Karnataka and Tamil Nadu sharing that same waters and have less water means upstream state might retain more water, then it has to go into the central government conflicts and everything. So the conflicts also can emerge into becoming more critical. So within a conflict regime, I'll be glad to study on how farmers themselves can adapt um, in different ways, and primarily diversifying beyond paddy, having some sort of a alternate systems where there'll be some sort of a adaptation possibilities. But I'm not very sure at this stage. But I will be glad to work with you on learning more about the system and then come up with some possible strategies for that. Absolutely.
Thank you, Dr. Timothy. Thank you. Thank you.
Sir, good evening, sir. Myself, Keetika, doing third PhD in Agri-Economics. So, talking about climate change and all the things, many of the papers are simulating more like nullifying the subsidies to fossil fuels because the United Nations is also stressing developing countries to reduce subsidies in fossil fuels. Practically, how it is possible in India, sir, in your view?
That's a good question. A lot of the climate strategies had been, I would say, pro-developed economies. And many of the developing economies, if they are going to implement a lot of the climate mitigation or even climate adaptation strategies, it actually adds to the cost because it's nothing is cost free. Who will pay for it? And that has been the big problem in more recent climate negotiation in Mexico, India. They opposed um, agreeing to certain strategies like complete carbon mitigation. That's only because that who will pay for it. And one of the strategy I recommend for developing economies is the developed economies should pay for it. Because the benefit is actually being shared by the whole global community, but when you already have gone through the developmental curve, um, but those countries which are actually slowly trying to get to that level, um, they should not bear the burden of the climate mitigation. And in order to do that, the developed economies should create a trust fund. I think they already have done that. It's a global green fund, and that fund is actually being used by developing economies to mitigate some of the carbon. And for example, many developing countries like Honduras had been trying to apply for those funds. So where you actually showcase what you'll be actually doing to mitigate carbon emissions, and it has worked. And that's why I'm saying, so primarily that carbon fund has to come from a developed economies. In an economic sense, that's the one thing, so we can actually force farmers to do things, but who will pay for it? And in order to ask that question, they have to be compensated some way. And in order to compensate, the money has to be collected from those who have benefited from that. And so a green fund is a really important solution for that.
So I'm Dr. Saravakumar, Professor Agricultural Economy. Thank you for your very good presentation. You have covered from scratch to policy formulation. Actually, our professor Sagar used to also asking same questions. So when we have used some econometric models, some of the variables very difficult to estimate. So we are controlling those variables, and we are estimating for temperature, climate level. We are showing the impacts. You have shown some complexity of the model. For a runoff model, it has several soil physical parameters. So will you get all the, is it possible to get all those parameters to include or incorporate in the model? Second one is we are using the downscaling the climate models. And if you are using that model, plugging those variables into automatic model, you will get all the results for even 1 kilometer or different resolutions. Now my question is, it's a very good academic exercise as far as my concern. So, how far these results are benefit useful to make the policy at local level? In our country, most in Tamil Nadu, the policy strategies have been formulated by administrators or politicians. From your research or from US, from these research results are effectively translated for local policy making or not? This is my question.
That's a very good question. There is a huge amount of, I would say, confidence in climate models. I would not say it's 100%, but it has been improving over time. So if you ask me about the climate models, like maybe 2 decades ago, some of the predictions, you're not you're less confident whether your temperature will. So there's always this percentage confidence associated with it. But over time, that confidence has been becoming better and better. So as we are now, I think one of the thing is, in much of the climate models are still at 1 kilometer or even 100 kilometer level resolution. So much more broader policies, we could make interpretations from that, but not at predicting at a farm level and making it much more confident on that, because you're essentially downscaling from a climate model. That's a primarily a statistical downscaling or dynamic downscaling, and that is a statistical exercise with some assumptions. We are assuming that your temperature and precipitation has some sort of a co-integrated parameter somewhere else, like surface temperature, sea surface temperature, and we use that one actually to downscale it. But the thing is, as long as those assumptions are tested in our policy models, we have to be very cautious about that. And in terms of application of these models, um, I would say when we don't have models for climate change impacts, let's say it was probably in before all these models had been used, or as well as simulation models and everything, we were actually trying to make guesses. And so our models actually give some sort of a general tendencies, general mean expectations and everything. So as long as we're very cognizant about that we are actually looking at a much more broader implications, whether the direction is this way or that way, uh, and 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 not to use it directly on applying it to a specific farm conditions or backyard. But what I have seen in my own experience, um, when one of my study was in maybe 12 years ago, that was probably first time I used simulation models to predict or bring in back to the backyard. That means how much impact it has on a local watershed. Even though it was people had been aware of impacts happening elsewhere, but when it says there's runoff is going to decrease, the summer precipitation is going to actually decrease, surface soil moisture is going to decrease, your snowmelt is going to go earlier. That was one of the predictions. And it has been occurring in the past decade. So people are now becoming aware of those things. So at a much more larger scale, we get some sort of guidance on policies. Um, and when we use that information, there's always a potential problem of. So when we use that one for econometrics, we probably have some sort of error propagation. The errors in a simulation model, the errors in measurements, they can actually increase or by adding it'll get added up as we are using the same data to actually use for multiple levels for econometrics. So as long as we test the assumptions in economics, that's one of the things. So you always go back and test what the sensitivity of that particular assumption is, and that's one of the things I use in terms of making sure we are right. And then the generalization of policy, we always have to have a caveat. When you make a policy decision, you should have a caveat and so saying this is based on this many years, this amount of resolution. And people should not just directly use it as some sort of a rule for a policy. And that's extremely important. As a scientist, we have to be explicit.
So good evening. I'm K. Shanmuga from Agriculture Extension. Could you explain about the possible scenarios of carbon sequestration and its policies that have been implemented in US, and also the possible scenario in India regarding farmers?
Farmers.
Yes, sir.
Very good question. That one I'm going to actually share some of my experience with one of the project I have in Honduras. Honduras have many small farmers have growing coffee, and the coffee prices has a very adverse impact on small farmers. They don't get sufficient profits. If you think about $8 Starbucks, that's a lot of money, but that is not going to the farmers. There's a lot of middlemen, a huge amount of price spread. The supply chain is extremely poor. That means once if it comes to when it goes out of that farm gate, primarily you're getting paid probably few cents. But once if it goes there's a procurer who gets from that particular farm gate, exports to the roaster, there'll be $4 added to that. And the roasters will actually supply to the retailers. That's another $4 or $5. There's a huge amount of price spread. All the work is done by a farmer for growing, uh, drying, processing. It's a huge amount of investment. So the farmers are actually going out of their profit is not sufficient. So the livelihood is not there. So one of the projects with four universities in the US and as well as one university in Honduras, we entered into we got a National Science Foundation grant to study how we could generate sustainability within a small farm, which is not easy. So what we are doing is we are proposing one system we developed, which is called as an integrated open canopy, where a farmer will retain forest and also have like 50% coffee. That means the coffee is of good quality, the yield is much more higher, but you maintain that forest. And that forest, what is the usefulness of it? For the carbon sequestration. So you can get value from carbon sales for the 50% forest, but also that forest has a lot of birds habitat. The birds are actually helpful in controlling the pests, which are devastating for coffee. It also, the forest acts as a buffer for rust. So rust is a big problem, coffee rust. So it spread of coffee rust from one farm to other is mitigated. So it's a really good win-win situation for farmers. But one additional sustainability question was the farmer will go out and clear a lot of trees. These are tropical forest trees. They clear it for burning wood so that they can dry coffee. So so one season they actually clear 1 acre of forest. So we're losing a lot of tropical forest. So for that, one alternative is to get solar dryers. So there was a patent for that. The solar dryers now, one of the suggestion is the solar dryer should be managed or operated by youth, but managed by women, because they are very efficient in actually having this whole operation. And so we are actually able to actually add equity to it, and we are actually procuring that forest carbon. The coffee also has soil carbon, and then farmers can actually sell that carbon credits in the open market. But the thing is, when one farmer cannot sell it to this, so you need like 100 farmers or 200 farmers to get this core carbon. So that is a source of revenue for farmers. So that is one thing probably India can also use, that they could actually sell that carbon. But for selling that carbon, there should be an organization on having a reputable carbon. What I mean by that, it's called as verifiable carbon market. It has to be verified. And one of the land use carbon is not, it's not, I would say they call it as a very risky, because land use you can harvest, it can go on fire, and so the carbon is not very risky. So if we can develop some sort of a cooperative way of selling carbon, it will be a source of revenue for Indian farmers too.
Good evening, sir. So you have discussed that the environment has the capability to self-organize itself in response to a disaster happen to it. So as we always look for empirical evidence, has there been any study, any empirical analysis done to prove this phenomenon? If so, how will we calculate its self-organizing abilities, sir?
Okay. So do you have any one specific like a disaster or?
No, sir. It is called
any
disaster.
So that's a good question. So these are called as resilience properties. Resilience properties is how do we know a system can get back to its original condition? So resilient property, one of them is self-organization. That means the elements themselves then come to get to that old level. Self-organization is much more efficient in natural systems, not in artificial systems, because they cannot self-organize. So I would say self-organized systems like nature, including a lot of natural elements, forestry, wetlands, those are self-regulating, having elements which can adapt and reorganize. Those are the ones we should think of. High biodiversity, high amount of natural systems built into the system. Forest cover is extremely important for resilience. And even the other resilience is social resilience, economic resilience. You need economic institutions to buffer any type of stress. The social resilience in people actually making decisions and innovations so that they can actually adjust to that particular stress, go back to the original conditions. So, for example, in Bangladesh, the social resilience was coming from family structure. They're able to borrow when there's a high amount of flood, their whole damage, they completely wiped out their house or anything, but they were able to cope because the coping is coming from the borrowing from their relatives. And so those types of resilience mechanisms should be there to, so in order to study that one, I would say the more artificial the system is, it's less self-organizing. And so one of the study I've been doing in urban systems in Massachusetts is the role of urban forests. The areas which have higher amount of urban forests had higher amount of resilience. They're able to handle hurricanes, water quality, storm, flooding, and everything much more better than those areas which are completely city-like infrastructure. So that's how it, empirical studies could be done based on those attributes.
I'm Karthikeyan, Professor in Head of Extension and Rural Sociology. So you made a very excellent presentation covering all latest dimensions of artificial intelligence and climate change. Excellent, good presentation. Actually, we are also interested in building the capacity of our students and faculty in the application of artificial intelligence in agriculture and other subject matter areas. So that is one area we are interested to collaborate with yes, and then we are also interested in research collaborations in the areas of climate change, carbon sequestration, and artificial intelligence applications. So
yes, yeah, yes, I'll be glad to collaborate. I think that's a really interesting application, and exploring those types of possibilities for extension. I think that's perfect. So Theodore is taking notes.
yeah.
So I think it's wonderful that there's so many avenues I could be involved as an alumni and also a professor from here long ago. I'd be glad to actually do that, and I think it's also a part of the MOU. So once the MOU is drawn, every year I also have to report to my university how the MOU is working. And our vice chancellor is so supportive of these collaborations, and I will be so glad to do that.
Okay, thank you very much.
Any other questions you have? Yeah. I think more questions from students have.
Good evening, sir. Good evening, sir. Good evening, sir.
See, please maintain silence, okay?
So myself, Divya from second MSc Agricultural Economics, sir. You have mentioned in one slide like application of big data in agriculture, and you have mentioned like the application was like weather forecasting and early warning system of flood and all. So I want to know that whether it is applied successfully in Tamil Nadu, sir, and I want to know the practical scenarios of that. We have saying like it is applied in weather forecasting. It is applied like analysis of pesticide application like that and also. So how can we find that practical applications, some practical scenarios of that, and whether it is successful in Tamil Nadu or yet to be, sir?
Early warning systems are really becoming popular in different areas. I visited the remote sensing department here. They have a really good early warning system for flood forecasting using remote sensing. So that type of applications are becoming very popular because you have to actually develop evidence, scientific evidence that there is this much amount of damage and which areas and everything, so that you can apply for disaster relief and everything. So there is, I was so impressed with the remote sensing team here, the department here, which has a lot of applications like that. The other one is the sensor technology, which has been also very popular in worldwide, whether it's water quality. I think you mentioned water quality for water treatment. So within drinking water, so you have sensors in every node, and if there is a high amount of contamination released, it automatically adds chlorine to the system. That type of a sensor attached to some control instruments also becoming a design type of a criteria. The other one is the sensors all along rivers and streams, sensors in forestry canopies, sensors in certain flow areas to capture certain changes in temperature, contamination loads. The design is primarily it has to be low cost in broad application. So like using like open source or low cost type of hardware becomes very important. But main thing is to have scientists work on optimizing that network design itself for sampling. So it's important.
I think we can. Okay, friends. So that Timothy will leave his email and contact details. Okay, so later also some of you may have your own clarifications as part of your research thesis kind of thing. So later you can very well contact him over mail, and we will also facilitate. So before some further formal things, so this as center cards. So we also keen in collaborating with the University of Massachusetts. So we have some potential areas where we can collaborate. So as you know, also since you are also Massachusetts economists and grown in the Department of Physical Economics, so so the Department of Physical Economics CARS is known for its excellence in natural resource and environmental economics. So the Department of Physical Economics, I think, does a lot of projects on natural resource and environmental economics. And in fact, I am the one. I'm also specializing in natural resource and environmental economics, particularly ecosystem services. So we can collaborate on natural resource and environmental economics, including the ecosystem valuation payment for ecosystem services. So as the PES is concerned, so it's well developed in developed countries like Japan and US and some of the European countries. Not in, it's very primitive stage in India. So since it is so basically so the PES is based on the beneficiary pays principle, and so we have a potential to exploit research on the PES and think of some policy measures. Since we advocate the organic farming and so some of the natural resource and environmental conservation policies, so the PEs would be a very good potential scope. I mean potential areas where we can collaborate. So I think so one area is the natural resource and environmental economics, including the payment for ecosystem services, watershed management, where we can think of the collaborative projects as well as the cost as a whole is concerned. And another one very important area is the recently, of course, the CARS scientists, both extension and economics, they work a lot on the artificial intelligence. And so recently we had established a lab, artificial intelligence in big data analytics lab, and so in our university we have so the big lot of big data. So one is the cost of cultivation scheme is there, and weather data. So when weather data we have ACRC, we have a big data there, and the the bioinformatics. So we have huge big data, so we can think of some kind of advanced analysis and capacity building also through student exchange and faculty exchange. So actually artificial intelligence Karthikeyan is working on, and so Dr. Purveshwaran probably you may be knowing. So he is actually in charge of AI and big data lab. And Dr. Sarana Kumar is working on climate science, so climate change. So there are so the potential thing we can think of, and so recently our honorable vice chancellor madam is encouraging all the directors and all the departments to explore possibilities for sending students to some of the advanced labs, advanced laboratories. So since you have established your own lab, so I think so the PhD students can be we can explore possibilities for sending PhD students in your lab so that they can integrate so the biophysical and the socioeconomic aspects into policy modeling. So those things to the course as a whole. So we have potential areas for collaboration. Okay. So this I think so today we had a very good session from our more usually so we used to admire from his performance. Okay. So it's very simply say that simple to say illustrious alumni, anyone can say, but he is a person like very few persons really actually proving that illustrious alumni. So in that sense, really we are very fortunate enough for Tim to have you here and listen to your wonderful lecture. Okay, so before the formal vote of thanks, on behalf of CARS and Tamil Nadu Agricultural University, it's our privilege to honor Dr. Timothy with a shawl and with a memento. அது ஆன் பண்ணுங்க. இது ஆன் பண்ணுங்க. அது ஆன் பண்ணுச்சா? இன்னும் வரலையே. சரி, please keep silence, please. Students from all the departments, 3 departments, then economics, extension, ARM, right? Right? Okay. Okay, now we have a final vote of thanks. Okay, invited by Senjil Madam, who was head the Department of Physical Economics, to give a final vote of thanks.
So, good evening, my dear students and faculty of course. So, for having this type of interactive sessions, our Vice Chancellor is encouraging in many ways throughout the university. So, on behalf of the Department of Agricultural Economics and CARS, first I extend my heartfelt thanks to our Vice Chancellor, who is very much interested in making our students ready for the future, to meet the challenges of future, and as well as preparing the faculty to make university number one in the whole continent. So I thank the Vice Chancellor for the gesture. And next, I am very much pleased to thank Professor Timothy, and so he is the alumnus of this directorate as well as the university, and he has given a very big picture of big data, climate change, watershed management, so whatnot. So he has given overall view of everything the people in the world is experiencing, how the data being generated and how it can be used. And I think the students also understand what type of data we are dealing with and what is its source, how we should preserve it, how it can collaborate, and how we can give a policy framework for protecting our Mother Earth. So I'm very thankful for that. Next, I thank all the university officers who has accepted our invitation, who has come here physically present and grace the occasion, as well as those who are online in remote campuses. And we have received some proposals for collaborations from other campuses also. So I'm really thankful for all the university officers who has joined us or who have joined in this endowment lecture. And also I thank all the heads of departments, both offline and online, who has also interacted and shown interest in getting collaborated with the universities in US where our speaker is working. And it's really a good time to have the interest our scientists show in collaborating with the universities abroad. And again, I thank all the scholars, assistant professors, associate professors, and especially the student scholars who has raised some questions, relevant and pertinent questions on the topic that the speaker has discussed. Really, I thank all the students, and I think this is a very big gathering I have seen ever. All the students from all the departments of COTS, and it is very interesting to know not only economics. So hereafter I can say this type of climate change or big data is not no more domain of economics alone. So what we need is only the data. We work together and give an output, maybe for policy or academic purpose. So in this way, I thank all the students, friends who has come here to spend their time. So nowadays, time is becoming very, very precious, both the students as well as teachers, and those who all spend their time, valuable time in attending this endowment lecture. And sorry, I forgot specifically the Dean PGS for giving this opportunity to invite Professor Timothy and interact with us. And so finally, I thank one and all who has attended this both offline and online and made this event a great, memorable one. Thank you, one and all.
Our special thanks to Professor Theodore sir and the Director Planning and Monitoring, so who are seriously involved in coordinating the visit of Timothy for a couple of days. Thank you so much, sir, Theodore sir and BPM sir. So on behalf of cards, we once again thank everyone, one and all. Okay. கருணாகரன் வந்திருக்காரு சார் தூரமா இருந்து, அவர் அப்புறம் நீங்க நல்லா டிஸ்கஸ் பண்ணிக்கங்க. ஓகே, தேங்க்யூ.